Okay, okay. Settle down. Get a seat. There's actually some free seats. So welcome back. Today we're going to continue what we were talking about last time, but let me remind you a little bit about what we were talking about. So we introduced the process notion last time, and a process basically is an operating system abstraction that we're going to be using from this point on to represent what's needed to run a single multi-threaded program. We said there were two parts to that. So there's the threads, which are kind of the concurrency piece, or you could think of them as the active piece that's executing instructions. And then there are the protected resources that are associated with the process, and that includes chunks of memory, device file handles, network sockets, all that sort of stuff are protected resources that are owned exclusively by that process. Why did we do that separation? Well, because the thread part can be discussed completely separately from the protection part, because you can have threads without protection and et cetera. Okay? And we also sort of gave you sort of this historical notion of a heavyweight process, which you don't really have to worry about too much anymore, but that's a process with only one thread. And that was kind of the way Unix and Multics and all of those originally started. And then here was this incredibly insightful diagram here that tells you the difference between single and multi-threaded processes. Single has one thread, multi-threaded process has multiple threads. And the thing that I'm going to spend a little bit more time on today, well, I'm going to spend a lot of time on threads today, but I want to make sure we understand kind of these unique pieces of the thread state. Now, the registers hopefully are pretty obvious to everybody. Those are basically the computational state that's being used by the thread, including the PC and so on. The stack is something that hopefully everybody's familiar with from 61C, but I'm going to make sure that everybody's familiar with it, because that kind of stuff sometimes disappears. Okay? So today, we're going to understand threads. We're going to talk about thread dispatching. So I'm going to start diving into the kernel a little bit and show you a model for what actually happens with threads. And we'll start talking about thread scheduling a little bit, although there's a whole lecture and a half or almost a week on scheduling in a little bit. So we can only touch on it today. Now, this was a diagram I popped up at the very end of the lecture and talked as fast as I possibly could to get it in before the end of the lecture. So let's spend a little more time on it. But what I wanted to show you is that real operating systems kind of fit into these four quadrants. So they may have one or more address spaces. Okay, and remember, these are the protection domains. And they may have one or many threads per address space. Okay, so for instance, early MS-DOS, other personal computers, Macintosh, kind of had one address space and one thread per address space, and it was a very sort of limited model. Okay, and these gave you the illusion that multiple things were going on, but it was usually faked in a way that you could easily tell, because you could crash the system extremely easily. Now, most embedded systems give you the thread abstraction, which is what our lecture for today is. Okay, but they don't necessarily give you the protection domains. Okay, so they don't necessarily protect each thread from the other one. Traditional Unix is, of course, over here. Here's the heavyweight process with one thread per address space and one thread, per process and many of them. And then kind of modern systems are down in this corner with many threads and many address spaces. Okay, any questions on that? All right. And then we kind of ask ourselves, where is Windows 95? I kind of have it over here with a question mark. And the answer is that there were a series of kind of half-protected operating systems where Microsoft was sort of introducing protection, but not really, because they had to be compatible with old 16-bit code. People wanted to run their Space Invaders code that they had gotten 2 decades earlier. And as a result, you could still crash these systems pretty easily if you knew what you were doing. Okay. Now, let's talk a little bit about thread state. So The states shared by all the threads in a process are the things like the contents of the memory, the global heap. Okay, so the way you can think of that is that the threads can communicate through this shared pot of memory, and in fact, most multi-threaded programming takes advantage of that, passes pointers to structures around and so on, and you will have a lot of fun with this. Perhaps I say that in quotes when we get to synchronization. Also things like I/O. Okay, so if you open files, all the threads that are in a process get to share those files and read and write from them. State that's private is kept in a structure called the thread control block. So that's going to be all of the unique state. And of course, it includes registers, and it includes the stack. And the question, of course, is what is the stack? Well, the stack is parameters, temporary variables, etc., return PCs, all of that stuff that the thread needs to correctly execute and that is not well defined at the beginning. So you don't know how much memory space you need because that's going to depend on how far you go recursively. And let me remind everybody, this is a 61C concept, but let me pull it back up on the board. If we have this piece of code, notice how A has a variable argument, temp, TMP, and if temp is less than 2, we call B, and B has no arguments, but it calls C, and C calls A of 2, and then when we're done with that, we call, these are done defining all this stuff, and we start everybody by calling A of 1. Okay, and what does that stack look like? Well, this is the definition for A, B, and C, so this is the first actual call. So we call A of 1, and what happens is a stack frame gets allocated for A, and space for instance, this variable temp is put on the stack. Okay, and the reason we allocate it is because if you notice in this stack, which by the way is going to grow downward in this diagram, we have two A's here. Here's an A and here's an A. And the reason is, of course, that if you call A of 1 and it calls B and B calls C and C calls A of 2, notice how in that call chain down the path there we end up with A again, with a different variable of temp. Okay? And so as we're calling, we're basically allocating things on the stack, and as we're returning, we're popping them off the stack. Okay? And notice also, by the way, I'm showing this return explicitly here. So what this says is that A is going to call, we're going to call A of 1, and when we're done, we're going to return by exiting the process. Okay? When we get into B, B says, in this first instance, A came through here called B. What happens when B is done? We return back to A plus 2, which really says kind of we're returning back to 2 lines into A. Okay, I'm kind of abstracting what this return is. It's really a 32-bit return value and everything, but I'm putting it in lines. Okay, does this make sense to everybody? Does that remind you of 61C? Okay, and so this stack is kind of growing and then shrinking and growing and shrinking. And if you have a procedure that calls itself forever, suppose we do B calls B, what probably happens is what? Stack overflow, segment fault. If it's an embedded system with no protection, perhaps what happens is it crashes in some mysterious way. But what's really going on here is in that case, we're allocate, and we're never deallocating, and so we got a problem. Okay, make sure, no questions on stacks, because we're going to kind of assume they make sense to everybody. We're all good on stacks. Now, of course, stacks are a little more complicated than this, because in order for us to compile code in different modules and link it together, the compiler has to have some stack discipline it's following. Okay, and so if, for instance, in MIPS, which is the processor that you get to emulate starting in project number 2, there is actually a stack calling convention which involves the 32 registers, okay, 0 to 31. And notice how I've got them categorized, and let me point out a couple of them. For instance, the 0 register is always 0. Okay, so this is a special register that if you write to it, nothing happens, and if you read to it, you always get 0. Read from it, you always get 0. We can talk about why that's later. But if you look at some other things, like for instance, registers 4 through 7 are actually called A0 through A3, and they're used for argument passing. So if you look back here, when we called A of 1, the first argument, temp, is probably put into the argument register 0, which, if you notice, would be register 4. Okay, so these are all things the compiler has to know in order to make the code work. Now, notice how the other things are classified here, for instance. So 8 through 15 here are called caller saves registers. 16 through 23 are called callee saves. And then here's another couple of temporaries, which are actually caller saves. And then we have a couple that are said to be reserved for the kernel. And then we have a few registers which are like pointer to global area. Okay, global variables are there. Stack pointer. That one should ring a bell with everybody. Frame pointer. What's a frame pointer? Points at the frame. Anybody know what a frame pointer is? Yeah. Yeah. So typically the stack pointer is actually the thing that's working its way down, and the frame pointer is typically pointing at a fixed offset into the frame, which is used to distinguish kind of the statically allocated stuff and the return variables from the things that are dynamically allocated. So it's used in conjunction with the stack pointer to use a good stack discipline, but you don't have to use the frame pointer. So what does this say? Well, before calling a new procedure, we have to save all the caller saves registers. That's these red ones. And the reason is because they're going to be called temporaries for the next procedure. It's going to be able to do anything it wants. And therefore, if I care about those values, I better save them before I call somebody, because they will clobber them. And then I've got to save V0 and V1. Okay, these are actually where the return values are put. And then I have to save RA, which is the return address. And then I can call. Okay, and after the return, we'll assume that all the callee saves registers, that's the green ones, are good. Why is that? Because if you ever want to use a green register, you've got to save it and restore it. Okay, that's why it's called callee saves. The one who's called saves them for you. We know that GPSP frame pointer okay, other things are trashed. Okay, why do I bother pointing this out? Just to let you know that in order to have a good stack discipline, somebody has to have come up with this set of constraints, and they're different for every processor and binary ABI and so on. But the GCC or whatever compiler you use needs to know this, and typically you as a person, unless you write assembly code, don't have to know this. Okay, because the compiler does it for you. But you have to know that you have to have a compatible set of compilers and linkers on a given piece of hardware, otherwise chaos ensues. Okay? Questions? Yeah?
Do the arguments get stored in the stack in memory or in the...
So in a typical RISC calling sequence, okay, this isn't true for the x86, but what often happens is, for instance, if you have 4 or less arguments, they may go into registers and never bother going into the stack, because there's no reason to. But usually as part of the stack discipline, you'll save room for them, so that if the procedure that's called needs to keep the arguments there but call somebody else, then they may save them out themselves. Okay, but in a procedure situation where you have a small number of arguments, you can often get by with never even putting the arguments on the stack. And that's usually with a RISC stack discipline. x86, unfortunately, has so few registers that usually everything goes on the stack. It's kind of the way it is. Good question. Anybody else? Yeah. As what? Yeah. Yeah, the base pointer is often used as a frame pointer, but there's actually, yeah, that can be used that way. Okay. Yeah. Say again?
If the arguments for the return value doesn't fit in a register, if it's too large, let's put it on the stack.
You know, oftentimes depends on what language you're dealing with. So languages like C and so on often don't let you really return much. And so they fit in the registers. If, on the other hand, you've got something that can return structures or something more interesting, then maybe it'd be put on the stack.
But they couldn't use that register because you couldn't follow a convention. You wouldn't know when to use either.
Yeah. So, yeah, the return values almost always in like a C language or something really are put in these registers. Okay, good. All right. So that's all I'm going to say about stacks, unless anybody has any more questions. But we're going to, actually, that's not all I'm going to say about stacks, but this is all I'm going to say about what they're for, and we're going to have to talk about how to allocate them in a moment. No. Don't want to talk about stack machines today. We'll save that for 152. So now, here we go. Here's our single-threaded example. Here we have a program, compute pi, put the result into pi.txt, and then print the class list. Okay, so what's wrong with this program? Yeah. Yeah, what? Well, not only does it never terminate, what else? Do we ever print the class list? No. Why? Well, because compute pi, it presumably keeps going forever. Okay, so this is a confused programmer. How many people here, I know you're too young, but have ever watched classic Star Trek? Okay. Do you remember the episode where Jack the Ripper gets in the computer and the way they drive him out is Spock asks the computer to turn all memory banks over to computing the last digit of pi? Remember that? You should check it out. It seemed to work. I mean, Jack the Ripper was gone. I mean, the computer didn't finish, but that was okay. So anyway, so this program's modeled after that. Now, what's the behavior here? Well, obviously, program never prints the class list, and that's because compute.pi never finishes. Okay. So here is a better version. Okay, why is this one better? Yes? Well, I don't know if I'd say it's the more interesting part, but it actually gets to print the class list. Yeah. However, yeah, no, that's right. So because we've got these two threads going in parallel, we actually get to print the class list. And the question, of course, is this going to be the behavior you want? If you were printing to the output, you'd probably get a jumble, right? Now, I've sort of implied that what's actually happening is the digits of pi are going into one file and the class list is going into another, and so maybe that's okay because you're not mixing them together. All right? So what does create thread do here? Well, this is kind of, it's a proxy for whatever thread package you've got, but they all have some sort of thread creation, and what this is doing is starting an independent thread running some procedure. Okay? And most thread packages have that notion. And what's the behavior? Well, now we actually see the class list. Okay, and hopefully this should behave as if we've got two separate CPUs, kind of, each executing together. Reality, of course, is that the CPUs are being interleaved. Okay, is everybody clear on that? Now, what's the memory footprint of this program? So suppose we stop the program and somehow look at it with a debugger. Well, we're going to say two sets of CPU registers. Why is that? Well, there's two threads and two thread control blocks, each with registers in them. Two sets of stacks. Okay, why is that? Because there are two threads. Very good. So questions. How do the stacks get positioned relative to one another? Yeah. So that's a great question. So these two threads are running in the same process. So what can they share? Well, they can share pretty much anything in memory. And in fact, they could, if they knew what they were looking for, maybe even grab values and mess each other up by writing their TCBs. Okay, now I'm going to argue for most of the next several lectures that the TCBs are in the kernel, so they couldn't even do that. But if it were a user-level thread package, they might be able to. So threads basically can trash each other pretty much any way they want, but because of the way the abstraction works, it's very hard for them to really screw each other's registers up that are stored in memory. But they can pretty much screw each other up by messing with their heaps anyway. So if you're interested in a malicious scenario here, that's really easy to derive. No problem. Okay? So how do we, back to the stacks here, how do we position them relative to each other? And why am I even asking that question? Yeah, some might require more memory than others. Okay, so what would that mean? Well, if we go back to our example, we'd have to look carefully at these two to see how recursive they are. Like compute pi, maybe that dives down many, many levels. Maybe print class list is not so recursive. I don't know, I'm making this up, right? Depends on the implementation. But that would say that maybe we need a really big stack for one of them and a not so big stack for the other one. Okay, but how do we know where to put the stacks? Do we put, the stacks on top of each other? Do we leave space between them? What? Well, but we don't have any virtual memory. This is unprotected. These two threads are in the same address space, so that's actually not an option. Yeah. Yeah, so maybe we have a predetermined stack size, 4K, 8K, something. What happens if we exceed it? Somebody give me a scenario if we exceed the stack size. Crash. That's a good scenario, right? If these two stacks are on top of each other and one of them is calling too many times, it could actually go into the other stack and completely mess it up. This is a really bad bug. Yeah?
Well, since if you're guaranteed one CPU and they're already interleaved, you definitely interleave the two stacks as well.
Well, interleaving the two stacks actually is not going to work according to the C calling sequence that I gave you with these registers. Because this typically, like the C language, assumes the stacks are linearly allocated.
Right, but you could change that around.
Yeah, so you could, every now and then, people often want to propose that we have stacks that are really linked rather than linear pieces of memory. So that could work. Can anybody suggest how we might notice with fairly good probability that things have gone too far and our stack is overflowed? Yeah.
I was saying you could put like a warning variable at the base of the second stack, and if you ever overwrote that, immediately you know that it's about to destroy the rest.
Okay. Now, that's a great idea. It probably wouldn't quite work the way you want, but in fact, oh, go ahead. Another suggestion. Yeah. Yeah, so you guys are kind of honing in on an idea here that might work. So assuming, even though the two threads are in the same process, we're going to have memory protection, and we could actually put what's called a guard page here, where if we ever tried to allocate beyond that, we'd cause a trap in using that guard page. Okay, so there are ways to notice that there's a problem. Unfortunately, if the thread is completely compiled by a bad compiler and it grabs an offset that's more than one page wide, it could jump over your guard page and you'd never notice. So these are only kind of, hopefully, things that help you. What size should we choose for the stacks? Well, again, that's hard to say. Sometimes there's a parameter you could put in, when you're compiling the program or linking it, or when you start your threads, it sort of say how much stack. And then, of course, we've been talking about what happens if we violate and how to catch them. All right, any questions on that? Yeah?
I didn't quite catch what you meant when you said that it may skip the guard page.
Yeah, so the way, when you call a procedure, what often happens is you save the stack pointer and the frame pointer. We won't talk about that. But then you decrement the stack pointer to make space. Okay, well, if you decrement it so far that the space you're getting jumps over the guard page, and you start writing down there, you could easily have written in the next stack and never noticed it.
Wouldn't a normal operating function always write to the vast majority of what it jumps?
Yeah, but it might be somewhere in the middle of that procedure, and by then you've screwed everything up, and maybe your debugging information's gone. So I'm not saying that always happens, but it's certainly plausible in this. Okay. Any other questions? Now, so what's our per thread state? So we talked about this thread control block. It's got the execution state, like the register is a program counter, the pointer to the stack. It's got scheduling info, which we will go into over the next several lectures. So things like what's its state, I'll say today, what's its priority, how much CPU time is it used. Accounting info, it might be possible that we're trying to judge how much CPU each thread's got to decide how to adjust our execution. Pointers to scheduling queues. Okay, you get to learn about that a little bit as you start diving into project 1. How about a pointer to the enclosing process control block? That might make sense, right? You might want to know what process you belong to, etc. That sounds like you might want a pointer to etc. as well, right? So in Nacho's, thread is a class that includes the TCB. So I would say probably a really good way when you start diving into Nacho's is to find the thread class. Okay, that might be a good thing to know about. In the next several lectures, and actually in Nacho's for now, the operating system's keeping track of the thread control blocks. So threads are going to be operating system scheduled entities. Later, we're going to talk about user-level thread packages where the threads are actually scheduled by user-level code, and you never have to go into the kernel to schedule them. We'll mention that in a little bit. Okay. So here's the life cycle of a thread or a process. Both kind of go through this life cycle. We talked about this last time. So it starts out new, which is threads being created. Then it gets put on the ready queue. It's ready to run. At some point, it's pulled off the ready queue by the scheduler, in which case it's running. Now, we're going to be saying for a little while we only have one CPU, so there's only one thread that's thread control block that's actually running at any time. And then, of course, eventually its time expires or it gives up the CPU in some other way, and then we'll go back to the ready queue. And we kind of go around here for a while executing. Okay? Did everybody catch that? You ready? Want to watch it again? Okay. Okay. Now, at some point, it might actually want to do some I/O, in which case it's going to go start the I/O and then go off on a waiting queue. So this waiting queue can be associated with the file it's going after. It could be associated with some network socket, whatever. But it's clearly that TCB is not executing. It's waiting. Okay? And eventually, the I/O completes. It gets put back on the ready queue, and now it's ready to run again. So only the threads that are either on the ready queue or running, and there's only one of those, are actually using CPU cycles. The rest of them are in queues somewhere. So this diagram's a little funny because it doesn't really tell you that there's lots of waiting queues. Okay? Then we start executing again. And eventually we're done and we terminate. Okay. So active threads are represented by their TCBs, and threads are in queues. Yeah, question? So they don't. So threads on the ready queue don't actually consume cycles, but if there are threads on the ready queue, there's at least one consuming cycles on the running queue. So basically, as long as you have at least one thread in this loop, maybe more, you know that you're using 100% of your CPU cycles for something. Okay. So thread not running, TCB somewhere else. Okay, so we have a separate queue typically for every device, signal, condition, whatever. So for instance, here's a bunch of queues. You might actually have the ready queue, which has a bunch of TCBs linked together, and these are the ones that are ready to execute. You might actually have, I don't know, a queue for a tape drive. I know they existed once. You might have queues for, notice it's empty, by the way, because nobody's using it. There might be links for the disk drive. It might be 2 disks. The second one doesn't have anybody using it. And there might be links for waiting on the network. And basically what this means is the ones that aren't on the ready queue are sitting here waiting for some signal to come in, wake them up, and put them back on this other queue. Okay, so you could say that a lot of what happens inside the operating system is queue management. We're going to manage the TCBs. Okay? Questions? Okay. A bit of trivia. So don't forget to go to your sections. I hope that worked out. Your first section in the real section rooms, everybody did okay? All right? Good. Did everybody find their section rooms? It's the big, ugly concrete building. You can't miss it. So in the interest of getting moving along, and I know not everybody likes Subversion anymore, but we're using Subversion in this class pretty much. There's information on the handouts page. Take a look, okay? Hopefully the Subversion server is all ready to go. Good, we got a thumbs up on that, so you should be able to start using it. Other things on the handouts page, interesting papers. So throughout the course, I will occasionally put up things for you to read, which are a little more on the research side. Oftentimes I put the reading in the lectures page, but not always. Also on the handouts page are some synchronization examples, which will be very useful. Probably, I'd say the intellectually hardest part of this class is probably synchronization. I don't know if my TAs would agree with me on that, probably. But I would say the best way to deal with synchronization, if you find it challenging, is to do as many examples as possible and get your TAs to do as many examples as possible. Okay? It's once you get in the right mindset, then synchronization's easy, something like that. The other thing, by the way, is previous solutions. I don't want to say finals. I don't know why I said that. Previous exams. So that may be useful to folks as we get into the midterm period. Now, I apologize for those of you that kept trying to go to Copy Central to find the missing reader. There was a little bit of miscommunication. It's actually at VIX. Okay, now VIX is kind of on the corner of Hearst and Euclid, but across the street from Copy Central. It's actually kind of down. I think you have to go downstairs a little bit. So it's right across from that delicious new sandwich shop on the corner. I have actually seen several of them in the room, so those of you who stumbled on it by accident, very good. But I apologize if anybody missed it. So, not Copy Central, VIX. RSS feeds are available. How many people have tried the webcast or listened to podcast type stuff? Okay, we have a few of you. Okay, if you go to the top of the lecture page, in addition to saying click here to see all of the videos, there's actually 2 RSS feeds which will give you links to the pages that have that actually have the video and audio separately. It's kind of interesting. I've actually gotten email at various times while I've been teaching this class of people listening to the class while jogging in Eastern Europe. I don't know. I guess I imagine them jogging, I don't know, past the factory or something and listening to OS. But, so people listen to these all over the place. So I guess you can get a lot out of it just listening, although the video version actually has the slides, which I would think would be easier. But I think I actually had somebody say they exercise while listening, too. I don't know. I don't think I had any people that listened to it to fall asleep, but it's possible as well. How many people are reading Nacho's code? Good. How many people have thought about reading Nacho's code? How many people have been avoiding thinking about starting to read Nacho's code? Okay. I would say, since officially on the schedule tomorrow is the start of the projects, I would get going. Okay? You can avoid it for one more day if you want, but you should start tomorrow. Okay. Any other administrivia questions? Okay. Our wait list is getting shorter. I actually didn't cancel it on Friday, but I have been told that we can absolutely not go over 10% of class size in this room, or they haul me away and then there'll be no teaching of the class. So, all right. If there are no more administrivia questions. Anybody not have a group yet? Okay. You should definitely send out mail on the list. Anybody have a small group that they could use another person? Send out, let's see if we can find you a group. Why don't you talk to your TA? Okay. Anybody else? All right, that's pretty good. Anybody in a, I won't ask that question. I was going to say in a group that isn't actually registered for the class, but I won't ask that question. Okay, let's talk about the dispatch loop. So here you go. I'm going to tell you everything that's in an operating system. Are you ready? Loop. Run thread, choose next thread, save state of CPU, load state of CPU. Loop forever. Okay, the class is now done. Your final will be on the 17th of December. So this is an infinite loop because what you do is over and over again you pick another thread and you run it. And perhaps one could argue that this is all the OS does, but don't argue about it too hard because you'd put me out of a job. I mean, how do you get out of this loop? Yes? Okay, you get out a sledgehammer. That would do it. What else? What's a little less destructive, but probably annoying as well? Yes?
Turn it off.
Turn it off. Okay, what else? Blue screen, right? Blue screen of death. I'm happy to say that even in this day and age, I still get a blue screen occasionally. Oh, yeah. Power to the people or something. So, yeah, we should exit this loop if we're shutting the machine down. That's a normal sort of exit. Or maybe if the machine does a panic and you get a blue screen. But in general, if it's not being shut down and you're not starting it up, it's basically running threads over and over again. Now, if there are no threads to run, which means the ready queue is empty, then perhaps this loop is really actually stuck in an idle loop or something. A lot of operating systems have something called the idle thread, which gets 100% of the CPU. Yes. Right? And that kind of a threading model is useful because it basically, when you're in the idle thread, you can put the CPU in low power state or something. So let's look at the run thread portion. So how do we actually run a thread? So we have to load its state, registers, PC, stack pointer, whatever, into the CPU. We have to load its environment, virtual memory space, and we jump to the PC. Now, of course, what I'm really talking about here is what does the operating system have to do? Most of the work of a thread, hopefully, is in the code the thread's running. So hopefully we're not spending most of our time doing this, right? That would be overhead. So how does the dispatcher get control back so that it can multiplex threads together, right? Suppose we've got two threads. Remember the compute pi example? If we compute pi forever, thread number 2 never gets to run. So it actually turns out there's two completely different classes of events, internal and external, that can be used to gain control back. One of them, the internal events, are typically cases where the thread returns control voluntarily. External events are things like timers and other interrupts where we interrupt the CPU and grab the CPU back. Okay? So let's talk about internal events. Here's a great example. You're computing along, and then you do a print. Or you're computing along, and you write to a file. That's an internal event where what you're doing is you're actively giving up the CPU because you said, I want to do some I/O. Okay, so when a thread goes to do I/O, that's a great time to pull another thread off the ready queue and start it running. Okay? Waiting on a signal. Well, here's another example where a thread is going to wait for another thread to do something. Well, effectively, you're getting put on a wait queue. You've given up your CPU. Okay? Here is the one we're going to talk a lot about for the rest of the lecture, called yield. So this is an example where the thread says, well, I'm still computing, but I'm going to give up the CPU for a little while. Okay, I'm going to yield the CPU. All right. Now, so here's an example of a compute pi that I would say is a good citizen version, where it's good in its loop. It computes the next digit, and then it yields, and then it computes the next digit, and it yields. Okay, so I'm assuming that we've got a system like the early MS-DOS or Macintosh that doesn't actually have preemption, where you have to yield, and this is sort of a good citizen. Can anybody tell me why it's not a great citizen? Yeah.
Never going to return.
Well, except that, you know, presumably if you're interested in computing pi, you were assuming it wasn't returning. Otherwise, you're a little confused. That's not what I'm getting at. Yeah.
You're never doing much work. You're only computing one digit, so the overhead is more than the actual work.
Okay, so the suggestion here is that you're never doing a lot of work. You're mostly yielding all the time. That actually might be true to start with, but was somebody else going to say something? Yes?
You might have the opposite effect, where it's only in theory that this function is going to yield, and in practice it might take it's like an hour to get the next digit in.
Okay. Does anybody know, I don't know if you've ever stared at how to compute pi by series, but it turns out that each successive digit takes longer and longer and longer and longer. So, in fact, this may be great at the beginning, but becomes a very bad citizen pretty rapidly because it's not yielding. Okay. Now, let's look at the stack now. Okay, so we're busy computing pi. We execute yield, and the question is, what happens in yield? Well, the first thing that happens is since the kernel, by the way, blue here means user mode. So since the kernel is the thing that's multiplexing our threads, the first thing we're going to have to do if we're yielding is we're going to have to get into the kernel. Okay, so that's why we go into this red color. So we make a system call, which basically goes into kernel mode and enters the kernel side of yield. Okay, and then that kernel yield calls run new thread, which then calls switch, which I'm going to explain all of these things in a second. So notice that the first thing to note is because we're scheduling threads in the kernel, we have to go into kernel mode to do it. Hopefully that's not surprising to everybody. Okay, and remember that these system calls are actually special trap instructions that go to special places in the kernel at the same time they go to kernel mode. Okay. So how do we run the new thread? Well, this run new thread procedure picks a new thread, switches the new thread with the current thread, does some thread housekeeping, which we'll talk about next lecture, and that's it. Okay, once again, that's all that it does, right? Now, obviously, there must be more. So what is switch doing? How do we switch to a new thread? We need to save all of the registers and all the state we care about so that we can maintain some sort of isolation for the threads so the threads don't, under their normal circumstances, interfere with each other, and somehow then switch in that state for another item or another thread and continue. But this may be not quite the way you think it is. So here we go. So let's look at something a little more interesting. Here's some code which has a procedure A which calls B, and procedure B just sits in a true loop going yield, 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 which is all overhead. And now let's suppose we have two threads and both of the threads are running this code. Okay, so we have this code. Now we're going to have two threads, and they're going to be yielding to each other. So we're going to go yield, 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 yield. Okay? Now, what does the stack look like? So suppose we're in thread S. So thread S has A. It has its own stack, by the way. It runs A, which calls B, which calls yield. And by the way, I'm going to ignore the kernel point of yield, because that's just putting too much stuff in our diagram. But in the kernel, we're going to run new thread and call switch. And what switch is going to do is switch is going to switch all of the registers for the thread S with all the registers for thread T. What happens? Well, part of the registers, one of the registers we switch is the stack pointer, which means by switching registers, suddenly we have a different stack. So after executing switch, kind of poof, we're in somewhere completely different, a different stack, just because we changed the register pointer. And now we return from switch, which returns from run new thread, which returns from yield, which goes back into B. Okay, but now we're in thread T. And then, of course, we're going to call yield and then run new thread, and switch will magically put us over here, and then we'll back our way out again. All right, now stare at that a little bit. How many people are completely confused by that diagram? Anybody? Okay. Ask me questions. What's confusing? Yeah.
Those rows that are in the thread and the stack, wouldn't those be actually, doesn't the kernel itself have its own stack?
Okay, so good question. So doesn't the kernel have its own stack? For the moment, let's say no. The answer is really yes, but for now, we're going to say no. So we're just going to we're only going to have 2 stacks rather than 4, because that would just get too complicated. Okay? But that's a good question. So right now, we don't have a separate kernel stack. Yes?
You only go, like in thread T, you only go back to B, right? Never return from B.
Yeah, so notice this code never returns from B. So yeah, we would never actually return back up here because the code doesn't do it. Yeah. So basically what's going to happen is this is going to seesaw back and forth and back and forth. But the thing that's kind of people find confusing about this kind of diagram is the fact that all we did in switch is we changed one set of registers for another, and because we did that, we were pointing at a completely different stack. And so if you look at the code here, A calls B, calls yield, calls new thread, calls switch, and we get over here, and then then switch returns, and we get back to run new thread, but we're kind of at this point in this stack. Okay, because if you think about it, if we hadn't changed the stack pointer, if we did yield, run new thread, switch, and then return, what would happen? We'd come back up this way, right? That'd be normal execution, except that because we switched the stack pointer, as we start returning up, we actually go back up this stack. Okay. Any other questions? Yeah.
On a previous slide, you said that you have the load state, load environment, and jump to PC. Is that all really just contained in switching rows?
So, yeah. So basically, let's see. You're talking about here, right? Oh, wait, what slide was that? So let's say the following here. If the threads are already running, this is what you see. If what you're interested in is starting a thread from scratch, that was more about starting the thread from scratch. And we'll talk about new threads next time. So right now, part of this diagram, which may be confusing to people, is I haven't told you how we get here. Right? These 2 thread stacks kind of just exist. I went poof, and they kind of existed. And we're just switching back and forth. So these 2 threads are actually on the ready and run queue, and they're alternating, and that's all that's going on. So you could think of this diagram as the steady state. Another question in the back?
So what happens the first time thread S calls thread T?
Ah, young Jedi, you worry about the first time way too much. So I will tell you next time about the first time. Think of it this way. Again, this is the steady state version. The short answer to your question is we actually fake thread T, before thread T's run the first time, we actually construct a stub here that has none of this stuff in it. And it's just a stub, so the first time we switch to a stub that then executes A and executes all that stuff. And so we put that little stub thing on the ready queue. That's the act of constructing the thread. And the first time we switch to it, it creates itself. But I'll show you that next time. OK, good. Isn't it amazing how many questions can be on such a simple slide? Any other questions? OK, shall I move on? All right, you'll have to ponder this. I'll actually bring this back briefly next time because I know there'll be questions that you catch in the next day. So, what does this switch thing look like? Well, it's very simple. Take the old registers, that's what these guys are here, and store them in some memory state. Load from some memory state into the registers, and then do a return. And what you don't see until I point it out to you is the MIPS ISA has actually got a special register called the RA register, or register 31, where the return address goes. So when you call somebody, the return address is actually in a register. And so what you've got here is we took the original return address and saved it aside, and we grabbed the return address of, say, thread T and put it into our return PC so that when we execute the return instruction, we actually return to where thread T wanted us to return to rather than where thread S was going to have us return to. Okay? Now, anybody here worried about, well, I'm trying to save registers, but I need a register to point at the TCBs, or nobody's worrying about that? Okay. You remember I showed you there's a couple of registers actually designated as kernel registers in the MIPS thing. And those are registers that if you as a user use them, you're guaranteed to have weird, unpredictable behavior because they're used by the kernel to save and restore stuff. Okay? All right. So what are some details on this? How many registers do we have to save and restore? Depends a lot on what architecture you've got. For MIPS, for instance, it might be 32 integer and maybe 32 float or whatever. Pentium might be 14 integer, 8 float, 8 SSE, 128-bit things, and SSE2, SSE3, SSE4. So there's a lot of other registers that got added on. Spark, might be 8 32-bit registers, 16 integer, a bunch of register windows, giving you 136 of these, so on. You get to Itanium, it might be 128, 64-bit integers, so on. So switch can vary a lot depending on the architecture. Depends on the processor. That shouldn't surprise anybody. Okay. Return PC is where the return should jump to. It's actually implemented as a jump. You can actually find the real switch .s in nachos if you look in the right places. You should, this is like a Where's Wally sort of thing. Find the switch.s. It's written in assembly. Not surprising because it's touching all of the registers explicitly. And of course, it's sort of it's kind of a magic thing because it's magically going from one thread to the next, but you can all understand it without invoking sort of the supernatural. Okay, are there any questions on this? All right. So one more thing. So what if you make a mistake when you implement switch? It won't work. Well, that's certainly true, but suppose you forget to save and restore register 4. What happens? Sometimes it doesn't work, sometimes it does. Okay, that's the worst type of bug. It's a non-deterministic bug. Okay, I actually suspect you will get to run into a few of these this term. Unfortunately, that sort of thing happens. But you get intermittent failures depending on whether the context switch happens at a point in time when register 4 matters. Because any of you taken any compiler classes know that registers are not always live all the time. Sometimes they're not live, and so trashing them is okay. Nobody will ever notice. Okay? Sometimes trashing them maybe causes a little bit of a mathematical error that you maybe would never notice. Okay, so this means that switch you got to implement very carefully. Okay, you get the wrong result without warning. It's kind of interesting. I've got a weather station on my roof that plugs into a home control system and into something else that's reading data from it all the time. And I think I've actually discovered a couple of weird synchronization problems, and I've been exchanging long emails with the manufacturers, and of course they never believe it. It's like, but I'm getting, when the load gets high, I'm getting very weird answers. Like temperature here in the Bay Area goes to 0. Okay, that doesn't happen too often. Okay, so unfortunately these kind of bugs are unpredictable, they're very hard to reproduce, and maybe even people won't believe you that they're happening. Okay, so the best thing, of course, is to make sure they never happen, and we'll try to help you with that later. Can you come up with an exhaustive test to test the switch code? Not really exhaustive, okay? There's kind of too many combinations and interleavings and all that sort of stuff. So the best you can do is have 12,000 programmers, no, that's not really true, but have several really good programmers stare at it many, many, many times over the course of many weeks and see that it looks right. Okay? Here's a cautionary tale that's kind of amusing. So there was a kernel developed by Digital Equipment Corporation called Topaz, and the people writing the kernel thought they were being really clever because in the switch statement, they saved one instruction, assuming that the kernel never got bigger than a megabyte. Now, okay, you got to go back in time a little bit, because I know you guys don't believe anything can be smaller than a gigabyte. But as long as the kernel was less than a megabyte, they could save this one instruction and all would be well. It would work fine. They documented it. What happened, do you think? Say again? People forgot, right? And time passed, people forgot. And they kept adding features to the kernel. And of course, nobody ever removes features. So as a result, the kernel eventually got bigger than a megabyte in size, 20 bits. And very weird behavior started happening. Okay, because you had something that was working fine, and the kernel just got 1 megabyte and 1 byte long, and suddenly it didn't work. But it only didn't work intermittently. Can you imagine that kind of horror story? Can you imagine you're the person that adds that last feature? And your last feature is perfect because you stared at it a long time, and suddenly the kernel doesn't work. So moral of this story is premature optimization is not always the right thing. Probably being careful to think that you got a correct solution is a much better thing. Okay? All right, we're going to take about a 3-minute break or 4-minute break and come back. So let's ask ourselves, so we had yield earlier. What happens if a thread blocks on I/O? Well, hopefully this doesn't surprise anybody that essentially it looks very similar. So I/O represents a system call. It's a different one than yield, but basically that system call goes into, say, the read system call, which then does its reading and then calls run new thread and switch. And essentially this looks the same as yield, right? Because we would then end up going to another thread. Now what's interesting about that, just try to picture that little seesaw diagram I had before the break. Basically, if we switch over here and execute some other thread, and when we switch back, at that point we'll actually end up returning from the read and we'll continue where we left off. So read kind of implicitly switches to another thread. The read happens because over time the disk blocks come in. Eventually we end up back on the run queue, and then we just return back out of read and we continue. Okay, just like we returned back out of yield in that previous example and continued. Now thread communication like signal and join, which you guys get to implement in Project 1. Networking, all sorts of I/O is very similar. Okay, questions? Now, what about external events? So what happens if the thread never does any I/O, never waits, and never yields? Well, if you're in the original Macintosh or Windows 3.1, what happens is you got a bunch of windows up and one of them keeps working and the other ones are all frozen. How many people have experienced this with a modern, something more modern than Windows 3.1? Yeah. So this is clearly not a protected operating system because it's very easy for a thread to go into an infinite loop and lock everybody up. So that's why, like for instance, Compute Pi forgets to ever print or yield. So how do we regain control? Well, we use external events. A great one is a timer interrupt. Okay, so what's an interrupt? We'll talk more about this next time, but an interrupt basically signals from hardware or software in some cases that basically reach in, grab the CPU out from under the thread, and go back into the kernel and start executing. So this is a kind of a hard grab the CPU away. Doesn't matter what it's doing, stop now. Okay, I have control. And timer. Okay, every machine pretty much has a hardware timer these days, and that hardware timer maybe goes off every 10 milliseconds or 100 milliseconds. And when that timer goes off, at that point, the thread is essentially forced to yield. Okay? And if we make sure that external events happen frequently enough, then we make sure that the illusion that the CPUs are being multiplexed actually happens and everybody makes progress. Okay? Now, we can show an example of a network interrupt. Let me just show you that here. So what is an interrupt like? Well, here's an example where we're running some user code, and I'm going to just show you some assembly here. So this is some assembly code that's executing along. And all of a sudden, an external interrupt happens, like the network interrupt. And what this really does is it causes a pipeline to stall right there and flush. We save the program counter and so that we can know how to return. We disable all interrupts and go to supervisor mode. So that basically is putting us in the kernel. And we'll talk more about this later. And then what's the kernel do? Well, the kernel does some stuff, which we'll talk about later. But eventually it runs a handler that's purely because of that network. So this might be something that basically takes the network packets out of the network and puts them into some buffers internally in sockets. And eventually it's done. And at that point it restores all the registers. Now notice we somewhere here we save the registers. And then we restore them. And that's so that whatever we do in here doesn't mess up the computation over here. When we're done, we do a return from interrupt, which restores the PC. We go back to user mode, and we continue where we left off. Okay? So basically, an interrupt is a hardware invoke context switch. There isn't necessarily a separate step to decide what runs next, because when we cause our interrupt, what we run next depends on which interrupt it is. So if it's the network interrupt, we run network interrupt code. If it's the disk, we run disk interrupt code. Part of what this code could do is say it's a disk interrupt that says the packet just came in. It may be that part of what we do is we take a TCB off of a wait queue, put it back on the ready queue. So that then, at the next actual timer interrupt, when we switch to some new thread, we actually might switch to a thread that had formerly been waiting. Okay? Are there any questions on this? Yeah.
So a network interrupt returns to the same process or thread that was currently running before interrupt.
You know, oftentimes things that are not timer interrupts all return back to the same thing that was running before. In principle, you could do a switch at that point as well. But usually the timer interrupt is the one that actually potentially invokes rescheduling. Yeah, question?
Just to make sure, network interrupts are raised every time you receive a packet?
So the simple answer to your question, are network interrupts run every time a packet's received, is yes. The more complicated answer is, if you've got a really high, like 10 gigabit per second Ethernet, then that would be too many interrupts per time. And so what happens is typically the first one causes an interrupt, and then the network interrupt handler empties all the packets out and then returns from interrupt at that point. And so while in principle you could get an interrupt for every packet, usually that's a little too much work for the machine at high speed. That's the longer answer to your question. You can ignore the longer answer if you want. Yeah?
In the previous slide, you mentioned software interrupts.
Yes.
Kind of explain what you mean by that.
So a software interrupt is basically the same process but invoked by software. And sometimes, for instance, there are even bits in the hardware interrupt controller that you can set that when you get into the right mode will actually cause the same sort of interrupt and return. But it's invoked by software rather than an external hardware event.
Does that imply there's like a separate thread of execution, like sending interrupts, or like if you only have one thread, you can kind of use?
Well, so, OK, so I don't want to get too in-depth with this, but suppose that some external event happens, and as part of this, we schedule a software interrupt here by setting some bit. But in this code that we were at, we're actually at a higher level of interrupt, so that software interrupt's being ignored. And then sometime we lower the interrupt priority level so that the software interrupt can be taken. So often the software interrupt is a way of deferring an interrupt when the priority gets low enough. But again, that's too much information, but you can take that away with you. Any other questions? It's good questions, though, by the way, so you guys are clearly thinking. Now, so timer is basically the solution to our dispatcher problem. Okay, so the timer forces the scheduling decisions. And so in this case, we have some routine that's busy executing, computing pi without yielding. The timer interrupt code does what? It does run new thread switch. Okay, poof. And now we've just basically yanked away the processor from a non-cooperative thread, and we haven't necessarily done anything too drastic to it because we're running something else, and later we can come back and continue. So it could be a perfectly OK mode in a modern operating system that the only way you get switched away is when the timer goes off. Okay, that's called preemption. All right. So, any questions? Now, so how do we choose which thread to run? Okay, we've been kind of ignoring that. So how does the dispatcher pick another thread? Well, there's a case, for instance, where there are no threads on the run queue, or on the ready queue, excuse me, or on the run queue. In that case, nothing happens. Nothing to run. Or if it's some operating system that has an idle thread, then that runs. Okay, question? No, stretch. Okay. All right, now, exactly one thread. That's easy. You could just continue running it, or not, not interrupt it at all, or you could actually go through switch with this one thread. But in that case, you're probably wasting overhead that you didn't need. Okay. More than one thread. Well, this is where things get interesting, right? Now you could say, well, the way I pick the next thread to run is I have some scheduling priorities. So I search through my list in the ready queue, and the things that are Of the things that are ready to run, I pick the one that's highest priority. Okay? How do I pick priorities? Well, I don't know. I could do last in, first out. Turns out this particular policy works for certain types of parallelism pretty well. I could pick one at random. Now, the problem with picking one at random is you want to make sure that you eventually get to everybody. Okay, but that's certainly a possibility. You could do FIFO, so you could just have a queue where you put the guy on the tail and pick the guy off the head. Okay, certainly this is probably the simplest policy. How could you choose between these? Say again? You could randomly choose a policy, yeah. Yeah. Yeah, it depends on what that's a great answer. It depends on what your computer's meant to do. Let me tell you this. We have a lecture and a half at least, I said this earlier, on scheduling. This process of deciding, it's bad terminology, this task, whatever, of deciding which guy to run next is dependent a lot on what you're trying to accomplish. And that's why there are many different types of scheduling algorithms. Some of them optimize for one thing and others optimize for another. Let me give you a couple examples. Real time. You might want to optimize for a real-time system by choosing the thing whose deadline is the soonest. Okay? Or maybe you are trying to be fair on a bunch of users, so you might pick a thread from a different user in such a way that every user gets equal CPU time. Okay, those are completely different policies, and we'll talk about those later. And by the way, there is a whole discussion that we'll have to have about what's a fair scheduler policy, because the notion of fair depends on what your goals are. We could have a priority queue which we keep sorted in priority order, and maybe a heap sort of some sort, and basically we pick the highest priority thing and run it. So that's another option. Okay, any questions? All right. So, I'm going to end a little bit early today. So in conclusion, so the state of a thread is contained in the TCB. All right, this is things like registers, program counter, stack pointer. We talked about some states the thread goes through: new, ready, running, waiting, terminated. Multi-threading provides a simple illusion of multiple CPUs, and I kind of gave you, hopefully, the beginnings of an idea how this works. And part of the magic there is by having a separate stack for every thread, we basically just have to switch in the new stack when we're multiplexing. Okay? And that's kind of a key part about what we're trying to do. And as a result, we can have this stack calling sequence thing just work between a bunch of threads multiplexing on the same CPU. We talked about the switch routine, which is this thing that absolutely positively has to be correct all the time, or you get weird non-deterministic bugs. And switch can actually be quite expensive depending on what your architecture is. Can somebody give me an optimization that you might do on an architecture that has a lot of registers to try to make switch be cheaper? Yeah. So we could have a single instruction that dumps all the registers out, and by the way, x86 kind of does things like that, but you still have the cost hidden underneath of sending everything to memory. So there is still a cost of sending those registers out. So how do we simplify, how could we lessen that cost? Yeah.
Keep track of which registers are actually used.
Okay, so we could keep track of which registers are used. Now the problem with that is that that's often hard to do really in general. Can somebody give me a very simple type of keeping track of registers in use that you might imagine doing? Yeah. Okay, we could have more than one set of registers. So anybody have any idea what there's at least two classes of registers in typical systems? One of them is integer. Floating point. So we could keep track of whether the code's doing any floating point at all and not save and restore floating point registers, and that could be a big savings. Okay? And we could do that by basically shutting off the floating point unit, and if you ever try to use it, you get a trap which then turns it back on and knows that the floating point registers are in use. So those are the kind of optimizations we might do because the switch routine is fundamentally at the center of the overhead of switching. Okay, not surprisingly. We talked about many scheduling options, and like I said, there will be a complete lecture and a half on that. And I think we're done. Now, are there any questions before we pack up? So start project 1. Dun, 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 dun. It is time. Readers are at Vic's copy.